Once we know that lines are parallel and we have a transversal running through them, then we can start talking about the properties of parallel lines and the angles and the segments that they create. In this module for parallel lines, we're going to focus on the relationships between the angles, and this video is going to start with corresponding angles and alternate interior angles. Before we get to that, we're going to talk about the properties of parallel lines and the angles created by transversals. And so geometrically, a property of a geometric object or a group of geometric objects is just a characteristic that applies to that object or to all of the objects in the group that is separate from its definition. It is true that parallel lines never intersect, but we wouldn't necessarily call that a property of parallel lines because that is how parallel lines are defined. Often when we talk about the properties of objects, it is something that is the result of its definition or is an extension or beyond what the definition merely says. As a part of this video, as we said, we're going to see the properties of corresponding angles and alternate interior angles when we have parallel lines and transversals. But first, we're going to do a quick review of proof and talk about lines in parallel planes. So here, a quick refresher, we're going to have the situation where plane X, plane Y, and plane Z intersect so that plane X is parallel to plane Y, plane Z intersects with plane X with line L, and plane Z intersects with plane Y at line N. And our goal is to prove that lines L and N are parallel. So first, I'm going to ask you to pause the video, do some strategizing about how you think we're going to go through this proof, come back when you're ready to hear the planning for it, see the proof, and then move on to corresponding and alternate interior angles. So we know that the definition of parallel lines is that they are lines that are coplanar that never intersect. While lines L and N are coplanar by definition because they're the intersections of plane Z with plane X and plane Y, so they are both in plane Z. That is the first part, they're coplanar, check. The second part is that they never intersect. And we are going to say that they never intersect because they are in planes that never intersect. So as we're going through the proof, to get to the fact that lines L and N are parallel, we need that they fit both parts of the definition of parallel lines, that they are coplanar and that they never intersect. So as we go through our proof, we're going to show exactly that. First, we can take all of these things that we say are given, and we're going to put them in the proof and call them given. For the sake of space, I'm not going to write those out because they're all right there. Well, like we said, we need to show that they're coplanar, so we can just say L and N are coplanar, which they are. Why? Because they are both in plane Z. Great. And that is a relatively easy thing to say because that's the definition of coplanar. They are both in plane Z. We also know that line L is in plane X and line N is in plane Y, and that X and Y are parallel. All that together, we can say L and N do not intersect because they are parts of parallel planes. And that is part of the definition of parallel planes. They never intersect, and their objects never intersect. Therefore, they are coplanar. They don't intersect. L is parallel to N by the definition of parallel lines. So, a quick refresher on proofs, a quick refresher on the definition of parallel lines, and now let's see some things that are true when we have parallel lines and transversals in the same plane. So, first, let's take a look at what we're looking at. Again, we have line L and M and transversal K, where we have 8 angles that are created, angles 1, 2, 3, 4, 5, 6, 7, 8, in this diagram by the intersection of transversal K with line L and line M. So the first thing that we're going to see is a postulate, meaning we accept it without proof, and that is something we call the corresponding angles postulate. If 2 parallel lines are cut by a transversal, then corresponding angles are congruent. So in this case, if we say the line L and line M are parallel, the corresponding angles postulate tells us that angle 1 is congruent to angle 5, because they are corresponding angles. It tells us that angle 2 is congruent to angle 6 because they are corresponding angles, and so too with angles 3 and 7 and with angles 4 and 8. And so taking this postulate without proof, we can then use it to show some other interesting things about the angles and the special pairs of angles that are created when you have lines and transversals. So before we move on to the next slide, go ahead, pause the video, copy down the diagram that we see with lines L, M, and K, as well as the text of the corresponding angles postulate. That is, if two parallel lines are cut by a transversal, then corresponding angles are congruent. Pause the video, come back when you're ready to see the next theorem, and then move on. So using the corresponding angles postulate, we can then prove what is often used as one of the most widely applied theorems as it relates to parallel lines and transversals, and that's the alternate interior angles theorem. That is, if two parallel lines are cut by a transversal, then alternate interior angles are congruent. So in this video, we are actually going to go through and prove the alternate interior angles theorem. But for right now, pause the video, copy this down, see if you can recognize using the angles that are in the diagram how we're going to go about this proof. Come back when you are ready to see the proof and wrap up the video. So the angles in this diagram are very intentionally created to lead to what we think to lead you in the direction of this proof. So statements, reasons, which I'm going to abbreviate there. We want to start by given that L is parallel to M, and we want to say that angle 3 is congruent to angle 2. And this is a relatively straightforward proof, because what we know is that angle 1 and angle 2 are corresponding angles, and by the corresponding angles postulate, angle 1 is congruent to angle 2 by the corresponding angles postulate, which I'm going to abbreviate here as CAP. Similarly, angle 1 and angle 3 are vertical angles. So angle 1 is congruent to angle 3 by the vertical angles theorem. That is, vertical angles are congruent. And finally, we have 1 congruent to 2 and 1 congruent to 3. So by the transitive property, we can just connect angle 2 and angle 3. By the transitive property or by substitution. So using the corresponding angles postulate, it's easy to see that in parallel lines, angles 3 and angle 2 must be congruent, and therefore that if parallel lines are cut by a transversal, then their alternate interior angles are congruent. Before we wrap up the video, we're going to see a quick application of that and calculate some missing values here. So before we go on for this, pause the video, see what you can do on your own here, and come back when you're ready to see the calculations for the values of those variables. So some of these calculations will use alternate interior angles or corresponding angles. Some of it will just use what we know about linear pairs. So the first thing that we can say, we have a 120-degree angle up here in the top corner, and that this 120-degree angle and z form a linear pair, so therefore z is equal to 60. Now we have z being corresponding angles or alternate interior angles with both 9y plus 33 and 7x minus 3. So we know that 9y plus 33 must be equal to 60. And that 7x minus 3 must be equal to 60. The 9y plus 33 because of the corresponding angles postulate. And 7x minus 3 because of the alternate interior angles theorem. So continuing along with solving these equations, if we're solving 9y plus 33 equals 60, that means that 9y is going to be equal to 27, and so therefore y is equal to 3. Now when we get to 7x minus 3, we add 3 to both sides, and we get to the fact that 7x is equal to 63, so x is equal to 9. And so using just the corresponding angles postulate and the alternate interior angles theorem, we can tell a lot about the angles that are in this diagram. And what your practice is going to be after this video is looking at a number of other different ways that we can talk about the relationships between angles that are created by parallel lines and transversals.